Hi everyone, and thank you for being here. I'm Aizierjiang, and today I'll be presenting our work, Chemo-IRL, DeFi Intent Discovery via Maximum Entropy Inverse Reinforcement Learning. This is joint work with Dr. Jerome and Dr. Sheng Wang across the University of Macau and the Guangdong Institute of Intelligent Science and Technology. In one sentence, we ask whether we can recover why a user is acting on a blockchain, their underlying goal, from a noisy sequence of transactions, and we do it by treating the problem as reward inference rather than classification. Let me start by laying out what we will cover. Here is the roadmap for the talk. I will begin with the motivation, why intent discovery in decentralized finance is genuinely hard and where existing methods fall short. Then I will walk through our methodology, the core of the paper, the chemotactic state design, and the maximum entropy IRL formulation. After that, I will cover the experimental setup, present the results and an ablation study, and finish with limitations and where we think this goes next. Let's begin with the motivation. So why is this problem hard in the first place? Decentralized finance runs on Ethereum and its layer 2 networks, an open and frankly adversarial financial environment where users almost never state their goals explicitly. The challenge is that a user's intent, the objective behind a sequence of transactions, is tangled up with low-level contract calls and with market conditions that change block by block. On top of that, the action identifiers we observe, things like protocol and function signatures, are often uniformative and sometimes deliberately obfuscated. And because these markets react to outside signals like news and social media, we are also dealing with real partial observability. So the core question we are really asking is this: can we recover why a user acts from what they did, even when the logged actions themselves are noisy? To answer that, it helps to see exactly where current approaches struggle. Most prior work approaches this through transaction level labeling. You annotate each atomic action with an intent label and classify. That's useful, but static classification tends to miss the temporal structure of what's actually going on. Here is the concrete example that I can show you. Imagine a user approves a router to spend USDC, swaps that USDC to VETH, deposits the VETH as collateral, and then borrows USDC against it. A static classifier looks at this and sees 4 separate unrelated intents. But step back, and the composite of those 4 steps is a single strategy, leveraged exposure. The meaning lies in the sequential composition, not in any one single action. That's why our stance is to cast intent discovery as sequential reward inference, not classification. Instead of guessing a label, we recover an explicit utility, a reward that explains the expert's behavior over the whole trajectory. The way we capture that temporal structure is inspired by an idea from biology. The inspiration is bacterial chemotaxis. A bacterium can't measure an absolute concentration very well, so instead it tends to sense how concentration is changing over time, comparing how versus a month ago, and biases its motion toward attractants based on that temporal gradient. We borrowed exactly that idea. We expose short horizon market trends to our agent through a temporal market gradient term, which I will write as nabla-tm, and the agent doesn't just see a static snapshot of the market. It sees which way things are moving. Here I want to be very clear about one thing because it matters for how you read the paper. This is a modeling motivation only, and we are not modeling biochemistry. And chemotaxis is not part of the IRL objective. It is simply the intuition that justified adding a temporal gradient feature to the state. With that intuition in place, let me position our work against the literature. Our work sits at the intersection of three areas. First, intent mining in blockchain. Prior work lifts raw call data and logs into semantic representations, and the team framework in particular proposes an intent taxonomy from transaction level signals. We reuse that taxonomy later. Second, inverse reinforcement learning. The classic goal is to recover a reward from expert demonstrations, maximum entropy IRL from Ziebart and colleagues, resolves the ambiguity in that problem by modeling expert behavior as a maximum entropy distribution. Modern distribution matching methods like Gale, Errol, Squill, and value dice build on this, and they become our baselines. Third, and this is the key conceptual link, recent work argues that simply matching demonstrations does not necessarily recover the task-relevant reward. The gap between data alignment and task alignment is precisely the trade-off we end up observing in our results. And finally, the chemotaxic literature, which, as I said, we use purely as an analogy. So, what exactly we contribute? Three things. We make three contributions. First, Chemo-IRL itself. We frame DeFi intent discovery as a sequential reward inference and instantiate maximum entropy IRL with a compact reward model. The two ingredients that make it ours are the temporal market gradient term in the state and deterministic semantic feature inference, phi of S and A. Second, GymDeFi, a gymnasium-compatible simulator for controlled, reproducible DeFi-style decision-making. Its distinctive feature is a configurable action obfuscation channel, a knob that lets us hide intent in a precise, measurable way. Third, a reproducible evaluation. We compare supervised, heuristic, and label-free methods using two contemporary metrics, reward recovery and downstream intent macro F1, and in doing so, we expose a trade-off between matching behavior and decoding discrete intent under heavy obfuscation. And let's get into how the method actually works. Here is the whole framework at a glance, and it's a loop. We start from DeFi protocols, which gives us a biomimetic state, ST. From that state, we extract semantic features, phi of S and A. Those features feed into our maximum, fed our maximum entropy IRL reward model, the red box, R theta, which is the heart of the system. The reward then scores candidate transactions. The selected action gets applied back to the protocols and the loop closes. The one subtlety worth flagging right now is that the transaction identifiers we read can be obfuscated. So the features and everything downstream are computed from possibly corrupted action labels. And the whole point is that the method has to be robust to that. Let me make each of these boxes precise, starting with the environment as a Markov decision process. We formalize the environment as a Markov decision process. The transitions are stochastic. They come from smart contract execution and market dynamics like reserve updates and changing lending rates. the true reward is unknown, and we use a discount factor gamma of 0.99, the state is where the chemotaxis ideas show up concretely. It's a composite vector with 3 parts concatenated. The user state UT, balances and approvals, the market state MT, prices, reserves, rates and gas, and the temporal gradient nabla TM, which is just the block-to-block finite difference of the market state, with 20 user dimensions and 22 market dimensions. And because the gradient adds another 22, the total state dimension is 64. The action is hierarchical. A protocol identifier, a function signature, and a discretized value bin that coarsely captures transaction size, with 5 protocols, 20 functions, signatures, and 10 value bins that gives the discrete action space of exactly 1000 actions. Now the most important design choice for our experiments, how we model intent being hidden. This is how we hide intent in a controlled way. The action we observe, AT, is drawn from a simple mixture with probability 1 minus P of BF. We see the clean, true action, but with probability P of BF, and the logged action is replaced by a uniformly random action from the whole space. The effect is intuitive. As P grows, the action identifiers carry less and less information, so a method that just reads the action labels has the rug pulled out from under it. Crucially, all learning and all evaluation happen on these observed transactions, like trajectories or transactions, features, and intent decoding only ever see the computed identifiers, never the clean ones. And throughout our experiments, we run at a deliberately high setting. P equals 0.7. So 70% of the time, the action label is pure noise. That's a stress test by design. Given that setup, here is the learning objective. Following Ziabart's work, we modeled the probability of a trajectory as proportional to the exponential of its discounted return under our reward. Higher reward trajectories are more likely, but distribution stays stochastic, which is exactly what we want given all the noise and partial observability. The reward itself is a function of the semantic features. R theta equals F theta of phi, where F theta is a small neural network. Now the normalizing constant Z theta is intractable to compute directly, so we don't. Instead, we use reward-guided rollouts as negative samples and optimize a contrastive surrogate. In plain terms, we push the expert demonstrations to have a higher discounted return than the trajectories our current policy samples, and we backpropagate through the reward network to do it. It's a simple tractable training signal that still respects the maximum entropy principle. Let me briefly cover the remaining pieces: the features, the simulator, and the training loop. 3 quick points. One on the left, The semantic feature map, a 21-dimensional vector, every entry deterministic and clipped between 0 and 1. It captures interpretable signals, swapping, lending, liquidity provision, yield seeking, governance, risk, and temporal patterns, and it's aligned with the theme intent categories. Importantly, it needs no external semantic model, which keeps everything reproducible. The DeFi environment maintains that 64-dimensional state, and each step decodes an action into its protocol, function, and value bin. Over the 1,000 action space episodes and their stochastically or at the horizon. So it will end eventually, either stochastically or at the horizon level. And training is a very simple alternating loop. Generate rollouts under the current reward. Select actions epsilon greedily. Mostly the argmax of the reward, occasionally random for exploration, and then update the reward to favor the experts. The one honest caveat in the note that argmax is a full sweep over all actions. It's fine at 1,000 actions but scale linearly. And I will come back to that in the limitations. Let's go forward, and that's the method. Let's show how it performs. Quickly, the experimental setup. Let's see that one on the data side, we generate 200 synthetic trajectories in DeFi, each between 5 and 15 steps. They span 6 intent classes. 3 simple ones like swap, lend, liquidity, and 3 complex multi-step ones, yield, leverage, LP. We apply obfuscation at 0.7. Use an 80-20 train test split with a fixed seed, and the labels are used only for evaluation and supervised baselines. The label-free methods never see them. We measure 2 things. First, macro F1 over the 6 classes reported overall and split into simple and complex intents, and for the reward learning methods. Those intent labels come from a fixed attribution-based decoder. We never train an extra classifier. Second, reward recovery error, or RRE. It measures how well the discounted feature expectations of our agents rollout match the experts, and lower is better. These 2 metrics capture different things, and that distinction is the whole story on the results side. Here are the methods we compare and the exact settings. We compare 3 families, 2 supervised methods, team, and a tuned supervised MLP, which get the true labels, so they serve as an upper bound. 1 heuristic, action frequency, which just majority votes over observed action categories, and the label-free reward learning methods, Sequential, linear, Gale, value dice, and our Chemo-IRL. Every method shares the same feature map, the same split, and the same obfuscated trajectories, so it's fair comparison. The table on the right has the exact configuration for the reproducibility, the ones worth knowing by heart: 200 trajectories, obfuscation 0.7, seed 42, state dimension 64, 1000 actions, discount 0.91, a small 2-layer reward network, and 60 training iterations. Everything is in the paper. And also, we open source the code. Let's look at the headline results. This is overall macro F1 for every method. The two blue bars on the left are the supervised method, team at 0.927, and the supervised MLP at 0.901. They have the labels, so think of them as the ceiling. Now look at the gray bar, the action frequency heuristic. It collapses to 0.092. That's the key message of this slide. When you obscure 70% of the action identifiers, just reading the action labels falls apart completely. On the right are the label-free methods, all working without any intent labels. Among these, SQL gets the highest macro F1, and our method, Chemo-IRL, the red bar, is right in the competitive range. But macro F1 is only half the picture. And the other half is where our method shines. On the right are the label-free methods, all working without any content, as I have emphasized. So let's bring in the second matrix and look at both together. Here is the full table with both matrices. Look at the RRE column on the right. Remember, lower is better. Our method, Chemo-IRL, achieves the lowest reward recovery error, 0.479. Compare that to SQL at 0.809, Linear Gale at 0.938, and Value Dice all the way up at 1.049. So in terms of actually matching the expert's behavior, Chemo-IRL is clearly the closest. But notice the tension. SQL has the highest label-free macro F1 at 0.474, even though its reward recovery is much worse than 1. How can that be? It's because the macro F1 here comes from a fixed post-hoc decoder. It's not something any of these methods optimize directly. So reward recovery and macro F1 can and do diverge. Recovering behavior well is not the same as decoding it into the right discrete label. That divergence is important enough that we visualize it directly. This plot makes the trade-off explicit. The horizontal axis is macro F1. Higher is better. The vertical axis is RE, and notice we inverted it so that lower error appears higher up. So good methods drift toward the top of the chart. Our method, the red marker, sits at the very top. Coordinates the, like here, sits at the very top and coordinates the whole thing here. And our method with 0.394 and 0.478, the best reward recovery of the group. SQL sits over the right, better macro F1, but it pays for it with substantially worse RRE. The takeaway is the honest one here. Better reward recovery does not automatically translate into the highest macro F1 under this fixed decoder. We think that's a useful finding, not a flaw. It tells you these two objectives need to be tracked separately. To check that our design choices actually matter, we ran an ablation. We removed two components. First, the temporal gradients, the chemotaxis ingredient. Taking them out drops overall macro F1 by 0.18, about a 32% relative fall, and this is the striking part. Complex intent performance collapse all the way to zero. The multi-step strategies become undetectable. Second, we replace the semantic features with random vectors that costs 0.15, roughly 27%, and again wipes out complex intent detection. So both design choices earn their place. The temporal sensing is what lets the model see multi-step strategies, and the semantic features carry real signal well beyond chance. Let me wrap up with what this means and where it's limited. The main takeaway is that reward recovery and macro F1 diverge. And the reason is that macro F1 depends on how well a decoder lines up with the taxonomy, not just on how good the reward is. Practically, that suggests a hybrid workflow. Use supervised labeling when you actually have labels, and lean on reward-based behavior analysis, things like preference inference, when you don't. I want to be upfront about the limitations. This is a controlled synthetic benchmark, so we make no direct real-world deployment claims, and it's also deliberately lightweight. 200 trajectories, a single split and seed, so we don't report variance, and the intent labels for reward methods come from a post hoc probe, which itself caps macro F1 and partly explains the trade-off we saw. Finally, that full action sweep scales linearly with the action space. Each of those points to future work. Harden the benchmark by decorrelating action identifiers from intent. Validate the real transaction traces. Swap the handcrafted features for LLM-assisted semantic extraction from raw cold data. Learn a proper intent decoder on top of the recovered rewards and extend to multi-agent male-aware setting. Let me bring all together. To conclude, we presented Chemo-IRL, which reframes DeFi intent discovery as sequential reward inference using maximum entropy IRL. The key idea is the temporal market gradient in the state, which lets the recovered reward depend on short horizon trends rather than static snapshots. And the headline empirical result on DeFi under heavy obfuscation at 0.7 Chemo-IRL achieves the lowest reward recovery error among all label-free baselines while staying competitive on macro F1. Along the way, we contribute the sequential reward inference formulation, a reproducible benchmark with a configurable obfuscation knob and an explicit account of the reward recovery versus intent decoding trade-off. The code is publicly available at the link shown here. And thank you so much for your attention. I'd be glad to take your questions. And these are some of the references that we utilized mainly in this presentation. Thanks for watching.